Hello guys, hope you're doing well. My name is Mahmoud Kiasri and welcome to the new chapter of Control. So at this chapter, we would like to dive down a little bit more to the fact that we have all of the tools that we need. We do have the Laplace transformation. We just move from the time domain to the frequency domain. We just solve the equation based on the poles and zeros. And so what? What then? So obviously, as you know, when we are talking about that control system, we need to have the input and output, and all of them is something related to time. So when we are using this kind of tools like the transfer function, like the Laplace one, like the state action, actually we are trying to simplify our work. But at the end of the day, we still have to come back to the x of t, and we have to know what would happen to the output based on the input, and everything should happen based on the time. So in this chapter, we would like to talk about those. We would like to talk about a little bit other tools that actually we can use, and also the very important factor about our control system, which is about the linearity. And as you guys remember, after some point, if we don't have a system that is going to be linear, it means that we cannot do most of the thing that we could do. In that point, we have to pivot. We have to improvise ourselves. We have to do a little bit of things. And this chapter, we are going to talk about it in detail. Without further ado, let's see. So as I just mentioned, in this chapter, we would like to talk about the superpowers. We would like to see the two ways that actually we see the world itself. So if you guys remember, for the previous chapter, we talked about some kind of the time domain that actually most of the time we don't like it because it's going to lead us to this some kind of some kind of computational characteristic of mathematics, and we would like to move it to the frequency domain. The reason we are doing that because it's going to be simple, and if we do have a couple of more systems that are working side by side, we can deal with it. After some point, we saw that we had some kind of limitations, especially when we're trying to implement it in the real world. We had some kind of saturation problem and so on and so forth. So this chapter, we are going to dedicate so much time that one. Again, let's have a little bit review. Why we use the Laplace? Because the Laplace was just actually a wormhole. It means that at the beginning of the day, we had the time domain that it was about the different equation. We saw that everything was a little bit challenging, so it means that we have to use the transfer function. So for the transfer function, or we use the transfer method, that we consider that initial conditions comes along for free, and then we are going to move to the new domain that we call it as the S domain. So at this point, instead of just using calculus, we are using the algebra. And then we are going to solve it. By solving it, it means that we are trying to find the relationship between input and output. And at the end of the day, we still have to back to the time, because we have to see based on the inputs what I could get for my output, still, if you're talking about the time itself. The very simple example was about the RC circuit. If you guys remember, the relationship between input and output was something like this. R times C times dV out divided by dt plus V out is equals to Vn. So for our parameters, imagine that we do have the RC as 0.5, the Vn is 1 volt, and the V out is 0. V out, by the way, as an initial condition. So for the algebra, it means that we have to convert this guy to what? To the Laplace, or using the Laplace transformation, and we have to convert it to the S domain. So it means that at this point, I do have 0.5 times S, V out S, plus V out S is equals to 1 over S. So at this point, I know that V out S is going to be 2 divided by S times S plus 2. So based on some kind of a specific input, which at this point was only 1 volt, I know that V out is going to follow this one. So if I would like to actually talk about that a little bit more, I have to some kind of see what would happen to the math, because we saw that we actually solved the V out in a frequency domain, but still I need to have it in time domain, because the time domain is actually giving me the whole diagram itself, and I can understand what would happen to the race time, what is about the steady state time, what's about the overshoot, and anything else. So the math over here was that the V out is equals to 2 divided by S times S plus 2. This is going to be a partial fractions. It means that if I would like to convert it to the form that I can convert it back to the time domain, I have to divide it into 2 fractions. And when I do that, you guys know that 1 over S actually was in frequency domain and its time domain is 1. And 1 over S plus 2 was actually e to the power of negative 2. Negative 2 e to the power negative 2t. So by having that, based on the input of 1 volt, my V out is going to be 1 subtracted by e to the power negative 2t. So based on the RC circuit, we know a couple of formulas about that t for some kind of 0.5 second is going to be considered as 1 tau, because tau for the RC is going to be just RC itself. And after 5 tau or after 4 tau, I somehow my kind of capacitor, because we're still talking about the capacitor, the V hat is going to somehow reach to its maximum itself. So the insight from this diagram is telling us that 3 lines of algebra precisely reveal the 2 seconds settling time. Imagine that in this scenario, instead of just having the RC as 0.5, I have the RC as 1. So obviously, as you can see over here, something would change. And instead of reaching to my 1 tau or 63%, I'm going to have something like this. It means that at this point, the timing that I had to reach the 63.2% is going to be something around here. If I assume that that guy is 1 second, then it means that it takes more time, and obviously it takes more time in order to reach to its fully charged itself. So if you guys remember, for the last part, we had what? We had 2 divided by s times s plus 2. And obviously reaching to this, from this guy to this guy, would be a little bit challenging. That's why we do have a shortcut. The shortcut is like this. Imagine that my transfer function is like that. F of s is going to be s plus 5 divided by s plus 1 times s plus 3. And I would like to convert it to what? I would like to convert it to 2 fractions. One, I know one of them has the poles of P1, another one has the poles of P2. But my main concern is about A and B. How I can do that? Simple. At the very beginning of the point, the only thing that you have to do is just put your fingers on one of these denominators. And after that, consider to solve your some kind of f of s based on the first pole that you just pulled your finger on. So the very first pole was f of -1, and we somehow cancel out the first pole. So we say that -1 plus 5, it means that instead of s, I just put -1 divided by -1 plus 3. So if you do that, you do have a number that is 2. The 2 is going to be coefficient for your first fraction. You can do the same thing for the next one to find the second fraction, second coefficient, and then you have 2 and -1. It means that your f of s just converted to 2 over s plus 1 subtracted by 1 divided by s plus 3. So obviously you can just convert it to 2 e to the power -t subtracted by e to the power -3t, and simple as that. So what would happen if you do have the state space and we would like to find what? We would like to find the metric exponential, or we would like to find e to the power of t. As you guys remember, we use this state equation while we do have the various input and obviously we do have various outputs. And x prime, or dx divided by t, or the rate of change over of x, is equals to a times x. A, as we just mentioned, is a matrix. Imagine that we do have 2 inputs to outputs. They're going to be 2 by 2, and A is the DNA of my system, and X is going to be my input. Again, imagine that I do have X1 and X2 as my input, and then I do have my B, which is going to be coefficient of U, which is my actual input itself. So X1 and X2 are going to be the current state, X prime is going to be rate of change, and U is going to be input itself. So if we assume right now, assume that my system is linear. So at this point, if I assume that my system is linear, I don't have any some kind of nonlinear equipment. For instance, if you're talking about the if you're talking about electrical circuit, we don't have any diode. We don't have any diode in it. We do have capacitors and inductors. If our system is linear, it means that we can use the superposition. Superposition means that I can divide my some kind of function into 2 parts: the zero input response and zero state response. By considering that, I can find what? I can find my phi of t, and then by using that, I can find the EA of t. So if I do have the zero input response, means that my U is going to be 0, and then my x of t is going to be phi of t times x of 0. And if I assume that I do have the zero state response, my some kind of the part of actually my e to the power of a of t, or the part of my some kind of state transition matrix that we know it as this guy, it just can be calculated like that. So imagine that I do have the example, and in my example, my A, or the matrix A, or the DNA of the system is 0, 1, -2, -3, and I know that the current state, or the initial state of my input, is going to be 1 and 0. So at this point, we would like to find e to the power of a at t, and let's move forward. So in this kind of questions, the very first thing that we have to do is to find the eigenvalues. If you guys remember, when we are talking about the when we are talking about this kind of question, when you have the matrix, our eigenvalues are going to play a role of poles, just like the S-domain function or some kind of using at the GS. We are going to have the lambda 1 and lambda 2, which are going to again play the role of the poles itself. So how we can find that? It's simple. The only thing that you have to do right now is find this matrix, which is A subtracted by lambda times I. A is the matrix that we have it, then lambda is going to be lambda 1, lambda 2, 0, and 0 is going to be, there's no lambda 1 and lambda 2, because obviously if you do that, or if you some kind of do the next step, we can see that lambda itself is going to enter it's going to enter the quadratic equation, and then you have two lambdas. So lambda 0, 0, like the diagonal matrix, that it's some kind of diagonal part is going to be a lambda. So we do have this, that lambda 0, 0 lambda is actually the combination of lambda and I itself. And I, it's just identity matrix, and the lambda, just we do have it over here. By just multiplying these two, I do have that guy. So I have to find what? I have to find the determinant of that specific matrix. As you guys know, the determinant of matrix, imagine that we do have A, B, C, D. The determinant of this guy is going to be what? It's going to be AD subtracted by B times C. So this is going to be determinant of specific matrix. So by finding the determinant matrix of this guy, I'm going to do what? I'm going to make it as 0, and then I can find my lambdas. Because we do have two inputs and two outputs, probably we are going to deal with two poles. So the determinant of A subtracted by lambda I is going to be what? It means that the determinant of, what was my A? 0, 1, negative 2, negative 3, subtracted by what? Lambda 0, lambda 0 itself is going to be 0. So if you calculate that, at the end of the day, you're going to have something like this. Lambda 2 plus 3 lambda plus 2 equals to 0. So obviously you know how to solve the quadratic equation. If you do that, you're going to have two lambdas. The very first one, the lambda 1 is going to be negative 1, and the second one, lambda 2, is going to be negative 2. So by knowing these two values, I just had my very first step. After that, we have to find the eigenvectors. For finding the eigenvectors, this means that the v1 and v2, what you should do, we have to solve an equation. That equation is going to be what? It's going to be A, just like this, is going to be A subtracted by lambda I times V, or some kind of something like that. We better to just call it as V equals to 0. So at the end of the day, I would like to find what? I would like to find V1 and V2. I do have I do have lambda 1 and lambda 2 is actually going to be negative 1 and negative 2, and I'm going to put it as 0. So it means that I have to some kind of make it as 0. Imagine that I do have my system itself, and for V1, so at this point, I do have the equation like this, and I already have my lambda 1 and lambda 2. I'm going to use both of them. For the very first step, I assume that my lambda 1 is going to be negative 1. So if I do have that, my A subtracted by lambda I is going to be what? Is going to be 0 subtracted by negative 1, negative 2, 1, negative 3 subtracted by negative 1 itself times the RV, or is going to be x1 and y1 equals to what? This guy equals to 0 itself. It means that if you simplify it, by the way, obviously this is very some kind of clear as a day why we do have that, because if you some kind of put your lambda as negative 1 over here inside of this guy, you can find this matrix. So by having that, we are going to have two equations. The very first one is related to x1 and another one is related to y1. And if you solve that, your x1 is going to be 1 and your y1 is going to be negative 1. So based on that, your very first vector v is going to be what? 1 and negative 1. This is going to be the first eigenvector. If we just do the same thing by considering the lambda 2, which is negative 2, which is going to be negative 2, I can find my x2 and y2. If you do the calculation, it is so simple. At the end of the day, you have your v2 as what? Is going to be 1 and negative 2. It means that your eigenvector, which is going to be the matrix of 2 by 2, is going to be based on 1 and v2. So right now, it's the time to find what? To find the main e to the power of a of t. So e to the power of at is going to be what? It's going to follow a very simple formula. Is v, which is going to be my eigenvectors, e to the power of dt times v to the power negative 1, or is going to be reciprocal of my matrix v or eigenvector. So the v is based on v1 and v2 was what? Let me just write it down. V was 1, 1, -1, and -2. And v to the power -1, or reciprocal of that guy, is going to be like this. As you guys remember, for a really brief review, if I do have a matrix like that, A, B, C, D, and if I would like to find the reciprocal of that guy, the only thing that I have to do, or find the inverse of that specific matrix, is going to be 1 divided by determinant of that specific matrix times by what? I have to change the place of D and A and make C and B, or multiply them by -1. So I do have D, A, -C, and -B. So if you do that, I mean, which is just a very, very simple calculation. If you do that one, your V to the power -1, or inverse of your matrix, is going to be what? Is going to be 2, 1, -1, and -1 itself. So I do have my V. I do have v to the power -1, or I do have the inverse. But what about e to the power of d of e to the power of dt actually equals to what? Equals to e to the power lambda 1 t 0, 0, e to the power lambda 2t. So since we do have the lambda 1 as -1 and lambda 2 as -2, I do have e to the power -t, 0, 0, e to the power -2t. So far, I have everything that I need. It means that my e to the power of a times t, let me just put another one over here. It means that at this point, as you guys remember, e to the power of at equals to v times e to the power of dt times to the power of times inverse of v. So based on all of the numbers that we found so far, 1, 1, -1, -2 is going to be my v. Then e to the power dt, e to the power -t, 0, e to the power -2t, 0, times my 2, 1, -1, and -1. Still, we do have the matrix 2 by 2 matrix. At the end of the day is going to be another 2 by 2 matrix. Multiply this one by another 2 by 2 matrix. And finally, your final value, or e to the power of at, or someone we know that's phi t, is going to be what? Is going to be like this. I'm going to just put the final value for you. Again, you can stop this video, try to find it, and you can compare your answer with mine to make sure it's going to be okay. 2 to the power -t, subtracted e to the power -2t, e to the power -t, subtracted by e to the power -2t, -2e to the power -t, plus 2e to the power -2t, and then e to the power -t, plus 2e to the power -2t. So this is going to be my phi t, and this is going to be final answer. I know it was a little bit long, but it actually worth. So the very final step is that actually we would like to find the x of t, because so far we found the phi of t. But what would happen to the x of t? The only thing that you have to do is actually x of t was equals to what? It was equals e to the power a of t times your x0, or your initial value itself. So I already have this one. What was my x of 0? It was 1 and 0. You can some kind of multiply this one by this one, because you have 2 by 2 matrix and you have 2 by 1. It means that at the end of the day, you are going to have the 2 by 1. It means that your x of t, or the final value of that, is going to be 2 to the power of -t subtracted by e to the power -2t, and then -2e to the power -t plus 2e to the power -2t. So that was the way that actually you can find what? Let's again look at the question. At this point, we would like to find the matrix exponential, or we would like to find the state equation. We can use these two values, or based on the superposition, based on the zero input response, and based on the zero state response, we can find the state transition matrix, and we can use it to find the x itself. So let's have another some kind of example over here, and imagine that our some kind of a is going to be 0, 1, -6, -5, and at the end of the day, we would like to find what? We would like to find the phi s, which is going to help us to find the phi t itself. Obviously, phi s is going to be si subtracted by a inverse, and you can find the phi s like this. And since you have that, you're going to use this one as a coefficient for all of them. So by using this way, you can again reach to the factor, reach to the place that you do have the 2 by 2 matrix, and for each of them, you're going to have what? For each of them, you're going to have one fraction. And then since you have the one fraction, you still have to convert it to what? To two fractions for each of these ones. And then when you have your S response, you can simply find what? You can simply find your time domain response. So again, these two ways, we're just looking at how we can use the normal way that we had it as a time domain, or you can use some kind of S domain to reach out to what? To the time domain. As you can see, the Laplace would be a little bit faster. At this point, I had planned to some kind of solve it for you, but I believe it's not that kind of challenging and hard. So the reality crash, because when we are talking about some kind of the systems, obviously not all systems are going to be the same. At some point, the system are going to be linear and I'm going to be nonlinear. But right now we do have the path, we do have a route. We can some kind of answer a couple of questions and see what would happen next and how I can use it for myself for some kind of have a little bit of prediction for my future response. So that's why we do have something like this. Okay, let's see at this flow chart. So the very first thing that I have to some kind of answer, the very first question that I have to answer for my system is that, is this system is going to be strictly linear? Because as I just told you, it's very important to consider this fact. If the system is linear, okay, that's fine. I can use a superposition, that is good. So if my answer is yes, means that analytical method works. So imagine that we do have the RC circuit that we use it all the time. The V out is going to be Vn times 1 subtracted by e to the power negative t over rc. So I can use the superposition based on the input some kind of zero state and based on the some kind of zero input. But if the answer is no, it means that superposition fails. As I just told you, again, superposition only works for the linear system, but doesn't mean that we have to stop. No, we are going to use some methods that we call as a linearization or numerical simulation. So at this point, I'm going to consider very small points. Imagine that I do have the dynamic system like this, but I'm going to find the specific and the small point. At this point is going to be linear. I'm going to do any kind of simulation or doing any kind of calculation based on that. Imagine that you do have the circuit, as I just told you, diode is going to be considered as the nonlinear component, and at this point I cannot do the superposition by itself. It means that superposition, as we know, adding effects works only for linear system. So nonlinear system is going to break the rule. So simple example again is going to be diode. A diode doesn't allow the current in reverse. It means that the response to 2-volt input is not going to be simply just 2 times the response to 1 volt itself. So another question that I have to ask for myself, by the way, when I talked about how we can make the system linearize, I'm going to talk about a couple of ways that actually we can do it. So is the system time varying? And it's another question that I have to ask for myself. If the system is time varying, it means that the matrix is going to be changed all the time, and we don't have any closed form of e to the power of a of t. e to the power of a of t is just assume that the matrix A is going to be just numbers. As we just saw, the matrix A was the 2 by 2, for instance, was just numbers. It wasn't an equation, or it wasn't some kind of the output based on that is going to be changed based on the time itself. So the very important thing that we have to consider over here, the analytical solution, assume that constant system matrices. If at changes with time, the formula for e to the power of t don't work. Imagine that you do have the system that you have the x prime, or some kind of the rate of change in x. Instead of just being a times x, it's going to be at times x. So at this point, we do have the at like this one, and at the end of the day, I cannot use the analytical situation because my at is not something constant, it is changing during the time. So if the answer to this question is the system's time varying was no, we have to ask another question for ourselves. Is the system massive? It means that it's some kind of more than 20 states. If it's the system is massive, means that I do have an issue. It means that at this point, imagine that we are talking about a very simple mechanical system, but instead of just having maybe 1 or 2 components, I'm going to have what? I'm going to have around more than 20 components. So calculating this guy, it means that I still can do that, but this calculating this guy means that I have to deal with a matrix of 20 by 20, which is going to be huge, and it doesn't work, or it doesn't actually some kind of worth it to do that. If the question was no, or if the answer was no, I still can do that, and this some kind of the system is feasible itself. So these are very important questions that you have to answer yourself while you're trying to do the simulation or do the calculation. And today we are going to talk about a couple of ways that is related to linearization. As I just mentioned, when we do have the nonlinear situation system like this line itself, as you can see, obviously I cannot solve it, or at least I cannot do the analytical method or the method that I knew using the superposition or some kind of focusing on the Laplace transformation. I cannot do that. So we are going to use a couple of methods in order to make a hypothetical some kind of linear condition. The very first one is something that we call as Euler method. As you can see over here, Euler method would assume that all of these some kind of linear lines that are connected to each other to make that this nonlinear are actually in the linearized part. It means that step by step by step, I assume that all of these guys are connected to each other, and based on the very, very simple formula that is like this, it means that x of t plus h, it means that the next step of x is going to be approximately equal to x of t, the current step, plus h, which is going to be what? Which is going to be my time, my some kind of step length times f of x of t and t, and I can find my next step. So by doing this, somehow I can mimic my system to replicate the actual system while I consider that guy is going to be what? While I consider that guy is linearized. But it's a very, very important thing that I have to consider is about the h, is how much the length should be if I would like to capture all of those points. If I would like to make sure at the end of the day, my system is going to be the same thing that it was, because obviously I don't want to use the linearization or any kind of method like the Euler method and ruin my system. At the end of the day, I'm doing this to simplify my work. At the same time, I would like my output, or the thing that I'm considering, should be as a real or the actual value that it was. Imagine that I do have the system that x prime is going to be negative 2x and x0 is 1, and I choose the step size or the step length as 0.5. So what would happen? X of 0.5, or the next step or the next value for x, is going to be 1, which was the initial value, plus h times my f of xt based on what? F of x based on the negative 2 and based on what? My current step, which was the 1 itself. So I'm going to have the 0. And the step number 2, if I still do that, I'm going to have the 0. So you see that h is equals to 0.5 is not going to be actual 1, because it is not going to be useful. My step 1 was 0 and step 2 is 0. So I'm not moving any place. So it doesn't worth it. That's why I have to make sure the step size that I'm choosing should be the right one. So the exact analytical answer for t is equals 0.5 is what? Is actually the Euler, or e of negative 1, which is approximately 0.368. And we have to what? The Euler confidently predicts as 0. So a massive failure due to a step size. And remember, we cannot choose whatever step size that we have. Why? Because if I choose the step size of 0.5, I'm going to have the system like this. While this white one, or this white line, was the actual value, the green one is going to be what? Is going to replicate that. But since the step size is so high, my system is going to be unstable itself.